Today I'll be presenting on Ankou. This is one of the feedback-based papers. It proposes a new fitness function, a new feedback mechanism. This is from ISCA 20 and is from a career research group called KAIST. So what is the problem that this paper is trying to solve? Modern-day grey box fuzzers like AFL primarily use code coverage as their feedback mechanism. And whilst coverage-based fuzzing strikes this good balance point between the results can get and so the cost and computational cost it requires, there still are some pitfalls to it. Primarily, you have this local optima problem where during fuzzing you can kind of get stuck in these areas where you aren't discovering new coverage points, and the way to move forward is either to have some kind of combinational set of expectations, some sort of particular path or some particular series of executions where you might have done every individual step before, but you haven't hit them in a specific combination. And that's kind of where this coverage-based fuzzing gets stuck, and this is kind of where the paper tries to step in and provide a solution that's not particularly expensive and isn't too different to existing methods, but still sheds some light and still finds a way around it. So a quick breakdown of what this presentation is going to cover. We're going to start by doing a quick overview of fuzzing, what it is, the general principles behind it. We're then going to sort of talk about feedback mechanisms and the particular fuzzing targets you're using in your feedback mechanisms to generate new seeds. We're then going to look at what the paper's solution is to the problem and how it tackles it. Then we're going to look at experimental results, how well did the paper perform and how well does their solution perform. And then we're just going to kind of look at the impact this new technique might have on fuzzing as a whole, and maybe some ways we can explore this idea further. So let's take a look at what fuzzing actually is. Broadly speaking, there are three types of fuzzing, although only rarely two of them are actually used in the real world. So in the most basic form, we have this thing called black box fuzzing. This is essentially just the core idea of fuzzing, which is that we're going to throw a bunch of random inputs into an application, and we're going to do that over and over and over, and we're going to hope that it's going to find some crashes. It's not very effective in terms of computational wise and in terms of time cost, but it is the core idea behind fuzzing, and it's essentially that if you do this long enough, you will find bugs. Where grey box and white box fuzzing come in is that they try to do this in a more reasonable time frame and with a more reasonable cost to it. With grey box fuzzing, which is kind of the most common form of it, you have some knowledge of your target application, and you use this knowledge to inform how you generate tests. So it's not just purely random, but you have some system for generating tests which are sort of moving in a direction. Ideally, that direction is towards crashes, but you don't necessarily know that. You just know that we are at least exploring new parts of the code, or we're doing something new with each test we generate. So then let's take a closer look at grey box fuzzing. The general pipeline of how grey box fuzzing works is we have our seed pool, which is usually just a list of past inputs we gave to the application, so past tests. We generate a new test, we run it through the target application, and we get some output. We then analyze this output in our fitness function, and from that we sort of decide, is this test getting closer to a crash, or at least does this test see something new in the code? So if it sees something new, we add it to our seed pool, and that kind of lets us move in a direction ideally towards new bugs. So how does this fitness function work? The fitness function acts as a type of filter, essentially. So we throw a bunch of tests at it, and its job is to let the interesting test cases through, the tests which are moving towards a crash, and to block the non-interesting tests. As if we let all tests through, that just means our seed pool would consist of a series of random tests, and then that's no more efficient than black box fuzzing. So how does the fitness function know which tests to keep and which tests to throw away? Well, with each test, we're going to have some data associated with it, whether that be like runtime, maybe a coverage score of how many lines it hit, maybe a branch count, or it will have a list of which branches it hit, but each test will have a bunch of data associated with it. So then the question becomes, which of these data points are interesting? Which of these data points are providing useful feedback that let us know which of them we should keep versus which of them we should throw away? That then leads us to the next point in this presentation, which is fuzzing targets. Essentially, how do we choose what metric we're using, and then what do we do with that metric to choose good tests over bad tests? And then as you can see from this diagram, different metrics have a different cost associated with them. So on one extreme, we kind of have no feedback, which is what black box fuzzes are doing. Since there's no feedback to analyze, there's no cost to that analysis. On the other extreme, we have taint analysis, which sort of uses data flow, and it follows the flow of variables through the application, and you sort of use that to see did we flow to new areas, did we reach new areas? This is extremely expensive and requires a lot of analysis. And now, why does this cost matter? Well, more computational time spent on analyzing metrics, on analyzing the feedback, means less time spent running tests, running trials, and ultimately, the more tests you run, the more likely you are to find bugs, regardless of how smart those tests are. So we want to find a good balance between the cost of analysis and the information we're getting from that analysis. Most modern-day fuzzers like AFL sit at this midpoint of coverage-based fuzzing, where it kind of looks either at branch coverage or code coverage or some kind of mixture between them. This is shown to be a good balance point between the cost of analysis and the results you get back from this analysis. But then the question becomes, what do you do with these coverage metrics, and how do you use that as your feedback mechanism? So how does coverage-based fuzzing work in application? In this example, we have a simple program where we need to hit a combination of conditions to cause a crash. So in this case, we need like a magic word of high exclamation mark, and if we hit all three of those branches, we'll then cause a crash. But we have to hit all three of them at the same time. It's not enough just to hit one or two. So let's say our first input is aim with a capital I. In that case, we'll hit the second branch. That means we'll hit some new coverage, and that test case will be added to the seed pool. Then say later on we have a new test of had with capital H. That one's going to hit the first branch, which is going to give us some new coverage, so we'll add that to the seed pool. So far, so good, sort of behaving as we would expect. But on this third case, we see where the problem lies. So in this case, we have him, so capital HI. We hit both branch 1 and 2. This test case is closer to causing the error, but it doesn't find any new coverage, so it doesn't get added to the seed pool, even though it's close to causing the crash and finding a bug. And this is the sort of local optimum problem I mentioned earlier, which coverage-based fuzzing has, and which this paper is trying to find a way around. So then the question becomes, what would he have to do to get around this problem? There are essentially three things the solution would need to do in order to get around this local optimum problem. We'd have to be able to quantify differences between traces, so we're not just relying on coverage, but we can actually see the difference, so we can actually measure some difference between runs. It has to be a relatively lightweight function so that it can be repeated multiple times at the scale that fuzzing requires, and the fitness function needs to adapt to the target program. Some parts of code are just going to be less interesting by their nature. Maybe it's like a print function, while loop, maybe it's part of the startup code, where you don't want to spend time trying to analyze the difference between the first 50 lines of code, where it's going to be pretty similar for all applications. You want to spend your time analyzing the more interesting parts where it starts branching off and starts closing on a potential error or a potentially hazardous spot in the code. So now let's take a look at how the paper proposes to solve the problem and what their implementation of that solution is. So again, the challenge, code coverage rewards new edges, but it doesn't look at the distinctiveness of different execution paths, which can lead to the fuzzer getting stuck in these local optima areas, where to get out of these local optimas and to get closer to the bug, they sort of need to add these middle test cases, which have the same coverage or cover the previous ground, but have a different path through those areas, which let them get closer to the bug. As a lot of bugs are dependent not just on the coverage, not just which lines of code they visit, but also in the order they visit them, and then how many sort of iterations they go through those specific lines. And that's what this paper tries to solve. But in order to do that, we need a new feedback mechanism and we need a new fitness function. And that's sort of where this paper's first idea comes in. They sort of propose that instead of looking at the coverage that a test goes through, first of all, AFL doesn't just give you the coverage points, but it can also give you how many times a particular test hit each branch. So that means we now have a series of values where it's not just Boolean, did we hit this branch, but also it's a count of how many times we hit a branch. They then use that data to generate vectors, where the dimensionality of the vector is the number of branches in the program, and the particular points on each of those vectors, and then the hit count. This allows us to view paths as vectors, and that means we can now compare tests as sort of points in space, and we can consider the difference between tests to be the distance between them. So let's say this particular point represented test 2. Test 2 hit branch 1 2 times and hit branch 2 9 times, and we can now plot this as a point in dimensional space. And now to compare this test to other tests, we would use distance as our function, as our fitness function. So it's our seed pool now becomes an area in this dimensional space, and our fitness function is now the distance between a test and previous tests in the seed pool. And if that distance is greater than some minimum we choose upon, we can then say this new test is further out into the space, is further out in this execution space, so is more likely to sort of be going in a new area. So we consider that interesting, and we then add that to the seed pool. But now if distance is our fitness function, that means sort of the cost of this fitness function is now just the cost of calculating distance. So how expensive is calculating distance? Well, essentially it's just based off Euclidean distance, or basically the Pythagorean theorem, where we just sort of take the square root of the difference between the squares in the vectors. However, now the cost of this function is dependent on the number of branches in an application, because the more branches there are, the higher the dimensionality and the more complex the equation becomes. Which is now sort of problematic because even for most sort of small applications, they're going to consist of hundreds of branches. So as you get some more complex, more real-world applications, your branch count sort of becomes too high for this to be a feasible feedback mechanism and function. So how can we get around that? So the paper introduces the idea of dynamic PCA, which builds off the idea of just PCA, which is principal component analysis, which is just it's a method of reducing the dimensionality in a vector. So going from maybe say a 100-dimensional vector to 20. So in this case, it's just all about compressing the number of branches in an application, or in particular, find the most interesting branches, look at the branches which sort of are more volatile, which change more, and focus in on them. So that solves the problem of calculating distance being costly, but that introduces a new problem where PCA itself is a costly procedure. So that's where dynamic PCA comes in. With dynamic PCA, instead of calculating the PCA and updating that value every time you add a new test to the seed pool, you only do that periodically to reduce the cost of that. And you also analyze the program itself and only try to reduce the dimensions of interesting branches to begin with. And by combining both of these ideas, you now have a usable fitness function. And then how does it look like when they implement it? Well, it's essentially just still a gray box fuzzer, and they've just replaced a coverage-based fitness function with a distance-based fitness function, where you're sort of passing in the trace of the program to see how effective that is, and then you add that to the seed pool, and then on a certain schedule, you then just recalculate your PCA, which is then just kind of the point in space that you're comparing new points to, and then checking the distance between the test to that point in space. So now, how well did Ankou perform? The paper's experimental results can kind of be summed up by this particular graph, where we're comparing the ratio of crashes between the distance-based fuzzing to the coverage-based fuzzing, which is the more traditional approaches which something like AFL is doing. So, a bit weird, but that's how they kind of choose to do it, so it's a bit of a weird graph, but it has all the information we need in there. So if we look at the left-hand side of the graph, we can see that the distance-based fuzzing is equivalent to, and in some cases a little worse, than the coverage-based fuzzing, but they're pretty equal, they're pretty comparable under these tests. So for about half the case, they're pretty equivalent. However, if we then look on the right side of the graph, we can see that in some cases we get up to a 4 times improvement, which is quite impressive, but we see this sort of general line of improvement. And now the question becomes, is it finding the same bugs quicker? So in the same given time, are we just finding bugs that the previous approach would find, or do we find new bugs? And that's where it's interesting in that this distance-based fuzzing doesn't only just find more bugs under under certain circumstances, but it also finds a different set of crashes, which is what we would kind of expect, because the whole purpose of this distance-based fuzzing was to sort of overcome the local optimum problem to try and find these specific bugs which were resistant to coverage-based fuzzing. So, knowing these results, what kind of impact can we sort of foresee this approach having, or how might this be used in the future? I think what this paper sort of proves is that this distance-based method it's useful in that not only can it find more bugs for certain applications than coverage-based fuzzing, given a period of time, but it's also able to find a different set of crashes, which might be resistant to the coverage-based technique. Knowing that, I think would prove useful for more established tools like AFL to implement this sort of distance-based coverage, either distance-based fuzzing, either in parallel to the coverage-based fuzzing, or maybe to sort of combine these two methods at the same time, or maybe you use coverage-based fuzzing for a bit until you get stuck in these local optima problems, and then you use this distance-based fuzzing to overcome that. And that way you kind of get the best of both worlds, where we're able to get the entirety of the sort of Venn diagram, not just the middle part, so we can get the entirety of this area of crashes. I think for maybe potential areas of exploration is that this paper sort of maps out these test cases in the sort of vector in this dimensional space. I think it would be interesting for further research to sort of build up these sort of dimensional spaces of test cases and sort of analyze the topology they sort of create. What I think could happen, or at least would be interesting, is maybe what you might find is in this dimensional space you might sort of find areas of sort of like flatness or similar topology, and then around crashes it may be that you sort of have dips or you have gradients which point towards crashes or point towards interesting behavior, and sort of analyzing this high dimensional space may be a way to sort of direct your fuzzing, or maybe a way to find more interesting cases which have higher promise. Thank you for watching this presentation. I hope you're able to learn something new and you're able to take something away and apply that to sort of future research and future ideas. Hope you have a good evening.